Hello, everybody. Okay, so I hope you have been enjoying doing trees and circuits and cycles and that kind of thing. So there's one more section in this chapter that we need to go over, and this one is a little bit different, okay? It's probably not something you're going to use, but it leads us to, at the very end of this chapter, something that's really kind of neat, okay? So we're looking at topology and fractals. Okay, so topology is not topography, okay? This is not about like making maps or looking at that. Topology is a mathematical subject, but this is a mathematical subject that we call abstract. So we know that in everyday life, we have the first dimension, the second dimension, and the third dimension. So a point would be the first dimension. Okay, so we don't deal with the first dimension very often because it would just be a bunch of points. But the second dimension would be if we were looking at lines. So everything would have to be flat. Okay, but we definitely could do it. So everything would be linear. So this is the second dimension. And when we graph, using like an XY graph in algebra, we're looking in two dimensions, X and Y. So two dimensions is definitely something we're used to. And then there's the third dimension. And the third dimension is where we give depth to our drawings, okay? So the third dimension. And that's the dimension that we live in, right? Everything that we have around us has depth to it. So then the fourth dimension is said to be time, okay? But we're not going to get into that. But what topology looks at is it looks at what we call nth dimension. So, like I said, it's not something we're going to use because we don't live in the nth dimension. But math can go past the third dimension. So there are rules that come into play as we go into further dimensions after the third dimension. And so topology is a whole study of these abstract, they don't really exist in our world, but they exist mathematically. Okay, now, like I said, you're like, why the hell do we need to learn this? And I totally get that. But the idea is that this is going to lead us to the end of this section, which is fractals, which is something we want to be aware of, okay? Okay, so in topology, two geometric figures are called topologically equivalent if one figure can be elastically stretched to form the other. Okay, so again, we're taking geometry and we're going to kind of stretch it into something that is not geometry, it's topology. So in topology, a circle, bear with me with my circle, we would say is topologically equivalent to a square. And now the reason why, obviously, geometrically, they're not the same, are they? Okay, they're not the same shape, okay, but topologically they are, because instead of thinking about them being drawn on the board here, think about as if they were a rubber band. I wish I had a rubber band right here. Okay, so consider them to be a rubber band. And if you take that rubber band that's in a circular shape and you put your fingers in it, could you make it into the shape of a circle. I mean, it's already a circle. Take the circle, put your fingers in it and pull it tight, and could you make it into the shape of a square? Okay. Now, could you then, if you wanted, take one finger out and turn it into a triangle? Okay. All right, so we're looking good here. So the one thing we couldn't do, though, is what if we wanted to turn it into a figure 8? Okay, now we don't get to go like this, okay? You don't get to do that. You just get to elastically stretch like this, okay? So if we wanted to turn it into a figure 8, though, is there anything you can do with your fingers without bending it around? Is there anything you can do with your fingers to get to this shape? And there's not. So this guy would not be equivalent. So what you're noticing is that it looks like basically if it has one area in between, that these all become equivalent to each other. Okay, so another one, would be like a trapezoid. Okay, we could turn that guy by pulling down on one half. Okay, so straightening out one half and then making a semicircle. Okay, so these guys would all be topologically equivalent. Now, that figure 8, if we wanted something equivalent to the figure 8, okay, we could do kind of some weird things here. Like we could do this, and that would be topologically equivalent to the figure 8. Now, at first you go, no, wait a minute, this isn't lines, and that is, but again, what you're thinking is, if I take a finger and I pull up here and I stretch out there, can I get a triangle up top? And then if I pull 2 fingers down in here like that, could I get a square on the bottom? Now, it might require more fingers than you actually have on your hand, but that's the idea behind this. Okay, so it's really stretching our dimensional thinking, okay, because in our dimensions, a circle and a square and a triangle and a trapezoid, they are not the same, but in topology, they are, okay? So then we say a curve is closed if it divides a plane into 3 disjoint sets. The interior, the exterior, and on the curve. On the curve. Okay, so this is just going a little bit further here to kind of use some of the terminology that they use, just in case this pops up in your homework somewhere. So closed means that when we look at a shape, okay, that shape cuts like we can think about it as the board, into 3 different spaces. There's the inside of the shape, there's the outside of the shape, and then there's on the shape, okay? Inside, outside, and on. So when we talk about the circle and the square and the triangle that are all topologically equivalent, they are all also closed, okay? Now, if we were to see something like a line, that's not a line, a squiggle then. Okay, if we saw a squiggle, now this squiggle is not closed, okay? It's not closed because there is no interior and exterior. So this isn't closed, but again, just because it's not closed doesn't mean it's not topologically equivalent to something else. So that little guy right there could be topologically equivalent to that. Okay, again, not closed, right? And if you take this again and just kind of stretch it, could you turn it into that shape? So again, there's a bunch of different shapes. You could pull them straight and get the straight line, couldn't you, in between them? All right, so the next question is, letters S and T I guess B is fine, be topologically equivalent. All right, so again, we're talking about topologically equivalent. So all that deals with is, can you stretch one letter and turn it into the other letter? Now, the thing here again is that we get really caught up on how we draw our letters, and most of us take two strokes to make a T and only one stroke to make an S. So at first you think, oh no, they can't be the same at all. But remember, if you can stretch and pull on this at all, could we take the S, so it's squiggly, pull it, and then pull it one way, and then pull it back the other way? So could we essentially make a T that looked like that? And we could, couldn't we? Okay? So that means the S and the T are topologically equivalent. So the answer to this is yes. But another way to look at this is to think about, are they closed or aren't they closed? Okay, so these guys are not closed, are they? Okay, they're not closed because there's no interior versus exterior, which means that we most definitely could turn one into the other. Okay, since they are both not closed, they can be topologically equivalent. Okay, how about a letter that could be topologically equivalent to P? All right, so P has one closed part, right? And then it has this line, and that line is okay. What we're looking at, of course, make my P a little bit normal looking, okay, is we're looking for another shape that has that one closed feature. So how about an A? Okay, now remember, we can pull on this line all we want. We can pull and we can stretch it. So if we put our finger up top, boop, we could get an A shape up there. And then if I pulled on this, I could get it to come down, couldn't I? Okay, so remember, very bendy and stretchy here. And so an A and a P, we would say, are topologically equivalent. Okay, another one here would be an R. Okay, again, not with my space that I leave there, but an R has one closed feature there. Now, another way to talk about this as opposed to closed and topologically equivalent is to talk about their genus. Okay. So the genus is how many cuts can you make before splitting the figure into two pieces. Okay, so now we're going to take our shape or our figure and we're going to like basically cut it in half or cut it in segments here. So let's start with that S there. Okay, so we want to know how many cuts you can make before it gets cut into two pieces. So look, if I make a cut like that, did I just cut the S into two pieces? Okay, I did, didn't I? So can we make any possible cut here on the S without it turning into two pieces? And we can't. So we would say that this has a genus of 0. Okay, because there's no cut that we can make that will stay as one piece. Okay, so as soon as we make one cut, we've turned it into two pieces. That means there's a genus of 0 because we can't make any cut. Same thing with the T, right? Anywhere you cut, one cut will turn it into two pieces, which means we can't make any cuts. So that's a genus of 0. Now, how about the P? Now you got to be careful when you look at these guys, so that you're really thinking about this, that it could be any one cut. So yes, if you cut here, that would turn it into 2 pieces, yes? But is there a place that you can cut that won't turn it into 2 pieces? So if we cut here, do we still have 1 piece? I mean, this end is kind of flappy now, but do we still have 1 piece? But now, no matter where we cut from here on out, here maybe, do we now have 2 pieces? Okay. So how many cuts could we make before we split it in 2 pieces? 1. So this would be a genus of 1. And again, come over here to the A and the R, and they are both also genus 1s. You can make 1 cut, okay? But as soon as you make a second cut here, you have two pieces. Okay, so they are genus 1. Now, that figure 8 that we had up here before, what would its genus be? So let's say we make 1 cut. Have we cut it into 2 pieces yet? Okay. Now, yes, if we make another cut on this bottom space here, it's going to be 2 pieces, but that's not the point. Could we make another cut like that and still leave it as 1 piece? Okay, so now it's flapper in the breeze there, but we've made 2 cuts and we still have 1 weird looking shape, but we still have 1 shape. But now, no matter from here on out, no matter where you cut, do we now have 2 pieces? Okay, we have this little piece and then that weird piece. So that means we could make 2 cuts before splitting it in half, which means this is a genus of 2. Okay, and a genus of 2 means that it's going to be topologically equivalent to any other shape that's a genus of 2. And so what that leads us to is what we call a donut is a coffee cup. Now, in our world that we're used to, there are 2 topological scientists that actually pop up in the weirdest place, and we think about them as being the weirdest creatures in the world, okay? But they are actually talking a lot of actual math, believe it or not, and that's Tweedledee and Tweedledum from Alice in Wonderland. So if you watch Alice in Wonderland and you look at Tweedledee and Tweedledum, they're always kind of telling each other riddles. But if you really listen to their riddles, you're going to start to see some of the math that we do in this class. And one of the things that they say to each other is, when is a donut a coffee cup? Okay, and in the show we just think, oh, they're just blabbing, it's no big deal, but they're actually talking about math. Okay, so consider a donut. Okay, give it some depth here. Okay. So there's the hole in the donut, right? Okay. So we would say that the donut is of genus 1 because you can make 1 cut or 1 bite and your donut stays in 1 piece, but as soon as you cut on the other side, then you get 2 pieces. So this is a genus 1. Now, a coffee cup looks like that, right? And at first people go, oh, well, it has 2 holes. But does it have 2 holes? Because let's look at this. This is most definitely a hole, isn't it? Okay, that one goes all the way through. But does this one where you put the liquid, does it actually go all the way through? It doesn't, does it? So what we've got here is another genus 1 because it only has the 1 closed in space. Okay, so these guys, we would say, are equivalent to each other. Now again, you go, no, they're not. So what I want you to do is I want you to think about the donut as dough, okay, before you've cooked it. So as dough, now the only thing we can't do is we can't get rid of that circle, but as you have this donut dough, okay, could you pull that circle off to one side and make it kind of skinny on one side, and then here you have all this extra dough over here. Okay, so remember, it's dough, so you could do this. So you could make one side skinny. Now, in this extra area where there's dough, could you push your finger into it? Okay, so could you kind of make an indent? So you have this hole over here. That hole has to stay, but then could you push your finger into the dough right in here, and could you push it in enough that you could actually put a liquid, something in there, and it would hold it? Okay, and you definitely could. So what happens is that you keep that like that. There's your hole, but then this dough that was over here, you start to mush it down, so that you can then put something in there. And now we haven't cut the dough in half, okay? We haven't done this, we haven't twisted the dough. All we do is we have the dough sitting there, we pull one side out and we push our hand down into it. So the shape of the dough has not been cut, it's only been stretched, which means a donut is a coffee cup. And you can look that up online and actually, they'll like show it to you how they shape it from one into the other. But that's the idea behind topology. Okay, so again, not something you're going to see on an everyday basis, but it leads us to something special, and that's the fractals. Fractals. So fractals, this is a relatively new branch of mathematics. So a lot of the math that we do has been around for hundreds or thousands of years. I mean, geometry has been around for thousands of years. The idea of the circle and pi and the circumference, that was from 4000 BC. So geometry is one of the oldest in the sciences, but even algebra is old. Calculus is not as old, but is old. But fractals have only been around for maybe 40 years. Okay, so this is something new that people, now the thing is that they've been around forever, but we've only noticed the mathematicalness of it in about the last 40 years, okay? So the definition of fractals is really weird, and you'll see why in a second. So it says this is the essence of a different dimension. All right, the essence of a different dimension is how they define fractals. So have you ever heard of anything mathematical that was defined like that? I mean, it's just like, what are we talking about here? How are we supposed to do this? But that's the thing with fractals, is that they are looking into another dimension. So when you see a fractal, you're not actually seeing our dimensions, you're seeing a different dimension. Sorry, I closed my book, I gotta get back to where it was. Hold. Okay, here, my spot. So the idea behind fractals is that as you look at them, there is a repeating pattern going on, and your mind and your eye is normally drawn right to it. And what you're seeing is kind of the difference between different dimensions. So as an example, we've got the fern here, and then we have this shape over here. But in the fern, in any fern frond, notice how that you've got the big fern, but then if you were to zoom in on just this little part right here, you're going to notice that it looks just the same as the big fern frond. If you zoom in further, you're going to notice that each little petal has the same shape as the big picture. And that's what a fractal is. Okay, so I'm going to do a little video to go along with this one on the computer, so that because it's really hard to draw fractals, okay, but so that you can see it on the computer screen. But we are going to draw one fractal, and I'm going to show you how this works. But don't worry, you're not going to have to draw fractals again, okay? So we're going to take a line segment. Of our donut and our coffee cup. So we're going to take a line segment there, and we're going to note the number of the segments, that we have, And then we're also going to make a note of their length, and we're just going to use random variables. Okay, so the number of segments here is n equals 1, and the length of the segment is r equals 1. Okay, so that's what we're going to start with. Now, what I want to do is I'm going to create a shape here. So I'm going to take this line segment like that, and I'm going to cut it into thirds. Okay. So now here, there are 3 line segments. Consider those to be little cuts. So our n is going to equal 3. And our r, though, this time, considering what the original was, isn't our r, the length of each one, isn't it 1/3 of the original? Okay, 1/3 of the original. So the n and the r, okay, go together, 3 and 1/3. Okay, then I'm going to take this one more time. And it's supposed to be exactly the same length as above. But I'm going to do this now. Okay. So what I've done is in that central space, I've popped it up and made a triangle there. Now, in this case, okay, how many line segments do we have now? So now I've changed the shape, so now there's 1, 2, 3, 4. So there's 4 line segments. But the thing is that every single line segment is still 1/3 of the original. So this is 1/3, that's supposed to be 1/3. Again, you gotta give my graph a break. That's 1/3, that's 1/3. So what happens is we end up with r equals still 1/3, even though the n has changed. Okay, so the n has changed to 4, and the 1/3 stayed the same. So what we're noticing here is at the beginning, this kind of 1-to-1 thing went on. The 3 and the 1/3 went together. Now things are looking a little bit weird, aren't they? Okay, so let me go one more step. Let me have to erase this, sorry. So we're going to take that same line segment, and I'm going to cut it into thirds like it was before, but then I'm even going to cut those guys into thirds. So it's going to go like this. Boop, 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 boop. Okay. Now again, I'll show you this on the computer where it's a lot neater, okay? I promise you. So here now, okay, what we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 little segments that we have made, okay? But then the R we want to see is how large is each segment compared to the original graph, okay? So each segment, if this was 1/3 and we cut it in half, this means that there would actually be 9 of these. Or sorry, we didn't cut it in half, we cut it in thirds. So there would be 9 of these. So there would be 1/9. So if we were to like line it up, cut, 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 cut. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1/9. Okay? But again, what we see is we've got an n of 16, and the r doesn't really go along with it. It's 1/9. So we had an n of 4 and an r of 1/3. But now what I want you to see is the fractal behind this, okay? So if you were to just forget about this part of the graph and just zoom in on that, forget about the rest of it. As you zoom in on that, does that look familiar to you? Does that look like what you've seen over here? Okay? And think about that. If you look at any little cut here, isn't it just that original? So what a fractal does is it starts to pull the dimensions apart, but what it does is it creates this pattern, this repeating pattern. So we could go one more time, and then that would put little triangles all along here. Okay, Everywhere where there's a flat space, it would put a triangle. Okay. And then again, you could zoom in further, and if you zoom in just right there, okay, do we have the original drawing again? Okay, so this is how a fractal works. But what they've discovered is that when it talks about dimensions, to see what dimension you're actually seeing is a formula that looks like this. Log of the capital N over the log of 1 over R. Okay, so log of capital N over log 1 over R. So if we wanted to see what dimension, not this little one where I made the little ones, but the 16 to 1/9, then what we would do is we would take log of 16 and divide that by log of 1 over 1/9. Okay. So when we do that in our calculator, because there's no way we're doing that by hand, divided by log, we get 1.26 dimension. Okay. So what we're actually seeing there is the 1.26 dimension. So when we see this fractal, that's what's popping up there, okay, which is kind of weird. And I know that on the board it really makes no sense. So I want to make sure that you do go and watch the video from the computer that I did along with this. But before I go to the computer, there's one other thing that I want to discuss before we go to the computer. And I want you to notice that when you look at this, doesn't there seem to be a very beautiful pattern? Okay, now again, on my drawing, it's not beautiful, go with it. Okay, but there's definitely a pattern that is occurring. And this looking into a dimension between the first and the second makes that it's really kind of this kind of essence of something very different. And you think that that pattern is very, very organized, but what you're actually going to see is that these fractals, while they are very organized, they are also very unorganized. So we're going to look at chaotic nature on the computer, okay? So yeah, so we'll get to that. But then you're going to see as we go to the computer all the different places where fractals show up. And even though they hadn't been studied until about 40 years ago or so, there's this mathematical sense that you're seeing something that's not in a dimension that we are in. Okay. Okay. So from here, go to the computer, a little lecture, and have a look at that one. Okay. Alrighty. Thanks, guys.